Let's start with something simple. Right now, wherever you are, lying in bed maybe, with the lights low and the world going quiet around you, there are particles inside your body that are connected to other particles somewhere else in the universe. And I don't mean connected by a wire or a signal or anything you could see or touch. I mean connected in a way that doesn't seem like it should be possible. Connected in a way that baffled the greatest minds of the 20th century. Connected in a way that Albert Einstein, arguably the smartest human being who ever lived, refused to accept until the day he died. That connection is called quantum entanglement. And tonight, we're going to talk about what it actually is, how it works, why it's real, and why Einstein was so deeply troubled by it that he spent the last 30 years of his life arguing against it. It's one of the strangest stories in all of science, part physics, part philosophy, part human drama. And by the time we're done, you'll understand not just the science, but why this particular mystery kept one of history's greatest thinkers up at night. So let's begin with the simplest version of the idea. Imagine you have two coins, ordinary coins, a penny and a nickel, let's say. You put them in separate envelopes, shuffle the envelopes around, and then you send one envelope to your friend across town. When you open your envelope and find the penny, you instantly know your friend has the nickel. That's not mysterious at all. The coins were always what they were. You just didn't know which was which until you looked. Now, quantum entanglement looks a little bit like that on the surface. You have two particles, two photons, say, or two electrons, and when you measure one, you instantly know something about the other, no matter how far apart they are. Sounds like the coin thing, right? You just didn't know what you had until you checked. But here's the thing, and this is where it gets genuinely strange. In the quantum version, those particles don't have definite properties until you measure them. They're not like the coins sitting in their envelopes, already heads or tails. In the quantum world, the particles are genuinely undecided. They exist in a kind of blur of possibilities, both options at once, neither option, something in between that doesn't have a name in everyday language. And then you measure one of them, and the instant you do, the very instant, the other one snaps into a definite state too. Not after a signal travels between them, not after some time delay, instantly. Even if the other particle is on the other side of the galaxy, even if it's a billion light years away, the moment you look at one, the other one knows. Think about what that means for a second. Nothing is supposed to travel faster than light. That's one of the most fundamental rules in all of physics. Einstein's own rule, from his theory of special relativity. Nothing, no signal, no information, no influence of any kind, can move faster than about 186,000 miles per second. That's roughly 300,000 kilometers per second. Light from the sun takes about 8 minutes to reach Earth, and nothing can make that trip faster. And yet here's this quantum effect that seems to connect two particles across any distance with no delay whatsoever, as if space doesn't matter, as if the distance between them is an illusion. Einstein hated this, and I mean really hated it. He called it spooky action at a distance, spukhafte Fernwirkung, in his native German, and he was not being complimentary. He thought there had to be something wrong with the theory, some missing piece, some hidden variable that would explain everything without resorting to this absurd, non-local, instantaneous connection between distant particles. Because if quantum entanglement was real, genuinely real, in the way the theory said it was, then the universe was far stranger than Einstein was willing to accept, and he'd spent his whole life making the universe make sense. But here's the twist that makes this story so compelling, the thing that elevates it from a physics debate to one of the great dramas in intellectual history. Einstein was wrong. Not about everything. His instincts were extraordinary, and the questions he asked were exactly the right ones to ask. But on this specific point, on whether entanglement was just a gap in our knowledge or something genuinely new and weird about reality, he was wrong. And we know he was wrong because, decades after his death, physicists designed experiments that could actually test the question. And the experiments sided with quantum mechanics. Every single time. That's what we're going to explore tonight. The full story of quantum entanglement. From the first glimmers of quantum theory in the early 1900s, through the fierce debates between Einstein and Niels Bohr that shook the foundations of physics, to the brilliant theoretical breakthrough of a quiet Irish physicist named John Bell, to the actual laboratory experiments that settled the question once and for all. Along the way, we'll talk about what entanglement really means, not the pop science version, not the oversimplified version, but the real, honest, slightly unsettling truth about what nature is actually doing when two particles become entangled. We'll meet the people who figured this out, learn why they fought so bitterly about it, and see how a mystery that Einstein dismissed as absurd turned out to be one of the most powerful and important ideas in all of physics. And I should warn you, the truth is weird. Not confusing weird, not complicated weird, but deeply philosophically weird. The kind of weird that makes you lie awake at night staring at the ceiling and wondering what reality even is, which, come to think of it, is a perfect state of mind for where you are right now. So let's start at the beginning. Not the beginning of entanglement specifically, but the beginning of quantum mechanics itself, because you can't understand why entanglement is so strange without understanding the revolution that made it possible. And that revolution started, fittingly enough, with light. At the turn of the 20th century, physics was in pretty good shape, or at least most physicists thought it was. The classical picture of the world, Newton's mechanics, Maxwell's electromagnetism, the laws of thermodynamics, seemed to explain just about everything. There were a few loose ends, sure, a couple of puzzling experimental results that didn't quite fit. But the general feeling was that the major framework was solid, and the future was about refining the details. Lord Kelvin, one of the most prominent physicists of the time, reportedly said something to the effect that the future of physics was just a matter of making more precise measurements. The big questions were settled. Physics was done. He was spectacularly wrong. Within a few years, the entire foundation of physics would crack open, and what came pouring out was so strange, so counterintuitive, so unlike anything anyone had ever imagined, that physicists are still arguing about what it means, more than a century later. The first crack appeared in 1900, when a German physicist named Max Planck was trying to solve a stubborn problem about how hot objects glow. You know this from everyday life. Heat up a piece of metal, and it starts to glow red, then orange, then yellow, then white as it gets hotter. Blacksmiths have known this for centuries. The classical theory of the time, based on Maxwell's electromagnetism and statistical mechanics, predicted how much light should come out at each color, at each frequency. And for low frequencies, the predictions matched beautifully. But for high frequencies, ultraviolet light and beyond, the classical theory went haywire. It predicted that a hot object should radiate infinite energy at high frequencies, which is obviously absurd. A hot piece of iron does not destroy the universe. This embarrassing failure was called the ultraviolet catastrophe, and it was more than just a minor discrepancy. It meant something was fundamentally wrong with the classical picture of how energy and radiation work. Planck found a fix, but it was a fix he didn't fully understand and wasn't entirely comfortable with. He proposed that energy isn't continuous. It doesn't flow in a smooth stream like water from a tap. Instead, it comes in tiny, discrete packets. He called these packets quanta, from the Latin word for how much. Each quantum of energy had a size proportional to the frequency of the radiation, higher frequency, bigger quantum. And he showed that if you assumed energy was quantized, if it came in these tiny chunks instead of flowing continuously, then the math worked perfectly. The ultraviolet catastrophe vanished. The predictions matched the experiments. But Planck didn't really believe in his own idea. He thought of it as a mathematical trick, a clever bookkeeping device that happened to give the right answer, but probably didn't reflect what was actually happening in nature. He expected someone would eventually find a way to get the same result without the quantization assumption. Physics would return to normal. He was wrong about that too. 5 years later, in 1905, a young patent clerk in Bern, Switzerland, took Planck's idea and ran with it. His name, of course, was Albert Einstein, and in one of 4 extraordinary papers he published that year, his Annus Mirabilis, his miracle year, any one of which would have made a lesser scientist's career, Einstein proposed that light itself is quantized. Not just the energy of vibrating atoms, but the light that those atoms emit. Light, Einstein argued, comes in tiny packets, particles of light, which we now call photons. Each photon carries a specific amount of energy, determined by its frequency. Higher frequency, more energy per photon. Lower frequency, less. A beam of light isn't a continuous wave. It's a stream of these tiny particles, each carrying its own little bundle of energy. Einstein used this idea to explain the photoelectric effect, the observation that when you shine light on certain metals, electrons get knocked loose. The classical theory predicted that brighter light should knock electrons loose with more energy. But that's not what happened. What actually mattered wasn't the brightness of the light, but its color, its frequency. Red light, no matter how bright, couldn't knock electrons off certain metals. But violet light, even dim violet light, could. Einstein's photon theory explained this beautifully. Each photon is a single packet of energy, and if the photon doesn't carry enough energy, if its frequency is too low, it can't dislodge an electron. More photons just means more attempts, not more energy per attempt. It's like throwing ping-pong balls at a coconut at the fair. Throwing more of them doesn't help if none of them is heavy enough to knock it off the stand. This was a radical idea. For over a century, the evidence had been overwhelming that light was a wave. Thomas Young had proved it back in 1801 with his famous double-slit experiment. Shoot light through 2 tiny slits, and you get an interference pattern on the other side, with alternating bands of bright and dark. That's what waves do. Particles don't do that. When ocean waves pass through 2 gaps in a seawall, they create that same crisscross pattern of reinforcement and cancellation. James Clerk Maxwell had then shown, in the 1860s, that light was an electromagnetic wave, a self-propagating ripple in electric and magnetic fields, traveling at a speed that, when he calculated it from the known constants of electricity and magnetism, turned out to exactly match the measured speed of light. Maxwell reportedly stared at the result and wrote that the agreement was too close to be a coincidence. Light must be electromagnetic radiation. The wave theory of light was one of the great triumphs of 19th century physics. And then, 20 years after Einstein's photon proposal, a young French aristocrat named Louis de Broglie turned the idea on its head. In his doctoral thesis in 1924, de Broglie proposed that wave-particle duality wasn't just a property of light, it was a property of everything. If light waves could behave like particles, then maybe particles could behave like waves. Electrons, protons, atoms, everything that we think of as solid, particulate matter, also has a wavelength. De Broglie's thesis examiners weren't sure what to make of it. They sent a copy to Einstein, who reportedly called it a very remarkable thesis, and endorsed the idea. Within a few years, electron diffraction was observed experimentally, confirming that electrons really do behave like waves. Matter has a wave nature, The universe, at its deepest level, doesn't distinguish between waves and particles. Everything is both. And now here was Einstein, saying light was also a particle. Not instead of a wave, also. Light was somehow both, a wave and a particle. Something that could spread out and interfere with itself like a wave, but also hit a detector with a sharp, localized click like a particle. This was the birth of wave-particle duality, one of the central mysteries of quantum mechanics. And it would only get stranger from there. But let's not get ahead of ourselves. Let's stay with Einstein for a moment, because here's an irony that runs through this entire story like a vein of gold. Einstein, the man who would later refuse to accept quantum entanglement, was one of the founders of quantum mechanics. He was there at the beginning. He helped build the theory. His 1905 paper on the photoelectric effect, the one that proposed light as particles, was one of the foundational stones of quantum physics. It's what won him the Nobel Prize in 1921, not relativity, which is what most people associate with Einstein, but quantum theory. He helped create the very thing he would spend decades fighting against. Let that sink in for a moment. The man who became quantum mechanics' most famous critic was also one of its founding fathers. Through the 1910s and 1920s, quantum mechanics took shape, piece by piece, insight by insight. Niels Bohr, a Danish physicist with a pipe always in hand and an extraordinary ability to hold contradictory ideas in his head simultaneously, proposed a quantum model of the atom in 1913. In his model, electrons orbited the nucleus only in certain allowed orbits. They couldn't exist in between. They could jump from one orbit to another, but they couldn't spiral gradually inward or drift gently outward. When an electron jumped from a higher orbit to a lower one, it emitted a photon with exactly the right energy to match the gap between the orbits. This explained the sharp spectral lines that atoms produce, those characteristic colors of light that each element emits when heated. Hydrogen glows red and blue and violet at very specific wavelengths, like a fingerprint, and Bohr's model explained why. But Bohr's model was still a patchwork. It worked beautifully for hydrogen and fairly well for a few other simple atoms, but it couldn't handle anything complicated. It was a brilliant patch on top of classical physics, not a new framework. The rules about which orbits were allowed seemed arbitrary, pulled from nowhere, justified only because they gave the right answer. The full framework, the one that would replace classical physics entirely at the atomic scale, came in the mid-1920s, in a blinding burst of creativity from a handful of young physicists who basically rebuilt physics from scratch in about 3 years. It was one of the most intense periods of intellectual revolution in human history. Werner Heisenberg, a German physicist barely into his 20s, developed matrix mechanics in 1925 while recovering from hay fever on the island of Helgoland in the North Sea. He'd gone to the island to escape his allergies, and in the salt air and solitude, he constructed a formulation of quantum mechanics based on abstract mathematical objects called matrices. It was strange, so strange that when he showed it to his mentor, Max Born, Born reportedly stared at the equations and said, "I think this is correct, but I don't understand it." Around the same time, the Austrian physicist Erwin Schrödinger developed wave mechanics, a different formulation based on a wave equation that described how quantum states evolve over time. Schrödinger's version was more intuitive to most physicists. It looked like the familiar wave equations of classical physics, just applied to something new. These two approaches looked completely different on the surface, but they turned out to be mathematically equivalent. Two languages for the same physics. Like describing a painting in English and in French. The words are different, the descriptions sound different, but the painting is the same. Paul Dirac, a British physicist of almost frightening mathematical ability, a man so quiet and precise that his colleagues joked about the Dirac unit of speech, defined as 1 word per hour, then showed how both approaches fit together in a more general framework. Within a few years, quantum mechanics had its foundation, and out of all this work emerged a picture of the subatomic world that was utterly unlike anything in classical physics. In the quantum world, particles don't have definite positions until you measure them. They don't have definite speeds until you measure them. They exist in what's called a superposition, a combination of all possible states at once. An electron doesn't orbit the nucleus in a neat circle like a tiny planet. Instead, it exists as a cloud of probability, a smeared-out wave function that tells you where you're likely to find the electron if you look, but not where it actually is before you look. Before you measure it, asking where the electron is doesn't even have a meaningful answer. It's not that the electron is somewhere and you just don't know where. It's that the electron genuinely isn't in any particular place. The concept of position simply doesn't apply until a measurement gives it one. This is captured in Heisenberg's uncertainty principle, which he formulated in 1927. The uncertainty principle says that there are pairs of properties, like position and momentum, or energy and time, that you can't simultaneously know with perfect precision. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our instruments. It's a fundamental feature of nature. The universe simply doesn't allow a particle to have both a perfectly defined position and a perfectly defined momentum at the same time. It's as if nature draws a line and says, "This much certainty, and no more." This was the part that started to bother Einstein, not the math. The math was elegant and it worked. What bothered him was the interpretation. What does it mean to say that a particle doesn't have a definite position until you measure it? Is the particle really in multiple places at once? Or do we just not know where it is? Is the uncertainty fundamental, built into the fabric of reality? Or is it just a reflection of our ignorance? These questions mattered enormously to Einstein. They weren't just academic quibbles. They were questions about the nature of reality itself. Niels Bohr and his colleagues in Copenhagen argued for what's now called the Copenhagen interpretation. In this view, the uncertainty is fundamental. The particle genuinely doesn't have a definite position until you measure it. The act of measurement doesn't reveal a pre-existing reality. It creates the reality. Before you look, the electron isn't anywhere in particular. When you look, it snaps into a definite state. This isn't just a gap in our knowledge. It's the way nature actually works. The wave function is the most complete description of reality that's possible. There's nothing behind it. No hidden layer. No deeper truth waiting to be uncovered. Einstein couldn't stomach this. He believed in an objective reality, a universe that exists and has definite properties whether or not anyone is looking at it. The moon exists whether or not someone is observing it. A tree falls in the forest whether or not anyone hears it. Particles have positions whether or not anyone measures them. Do you really believe the moon is not there when nobody looks at it? He once asked his friend Abraham Pace during a walk at Princeton. It was a rhetorical question, but it captured his deep conviction that the universe doesn't need observers to be real. Things are what they are, regardless of measurement. Physics should describe that reality, not just our observations of it. The debate between Einstein and Bohr became the stuff of legend. They went back and forth for years, especially at the Solvay conferences, those invitation-only gatherings of the world's top physicists in Brussels. Einstein would arrive at breakfast with a new thought experiment, designed to prove that quantum mechanics was inconsistent or incomplete. And Bohr would spend the day pacing, chain-smoking, muttering to himself, and then appear at dinner with a response showing that Einstein's argument contained a subtle flaw. This happened again and again. Einstein would attack, Bohr would defend, and quantum mechanics would survive. The most famous of these exchanges took place at the 1927 and 1930 Solvay conferences. In 1927, Einstein proposed a thought experiment involving the double slit. He argued you could determine which slit a particle went through without disturbing the interference pattern, which would violate the uncertainty principle. Bohr showed, after a tense evening of calculation, that the recoil of the slits themselves would introduce just enough uncertainty to preserve the principle. In 1930, Einstein came back with an even more ingenious argument: a photon box that could supposedly measure both the energy of a photon and the time of its release, violating the energy-time uncertainty relation. This one rattled Bohr badly. He couldn't sleep, but by morning, he had found the answer. And ironically, it involved Einstein's own general theory of relativity. The gravitational redshift caused by the box's weight change would introduce an uncertainty in the time measurement, preserving Heisenberg's principle. Einstein had been beaten by his own theory. After these encounters, something shifted in Einstein. He was getting older. He had moved to the United States in 1933, fleeing the rise of Nazism, and settled at the Institute for Advanced Study in Princeton, New Jersey, a quiet, leafy town that couldn't have been more different from the bustling Berlin he'd left behind. At the Institute, he had no teaching obligations, no committee meetings, no administrative duties, just time to think. And what he thought about, increasingly, was whether quantum mechanics was really the last word on the nature of reality. He stopped trying to show that quantum mechanics was internally inconsistent. Bohr had beaten back those arguments at the Solvay conferences. The math worked. The predictions were right. Einstein accepted that. But he shifted tactics. Instead of arguing that quantum mechanics was wrong, he argued that it was incomplete, that it was a perfectly good theory as far as it went, but it wasn't the whole story. There was more to reality than quantum mechanics was telling us, and entanglement was his weapon. In 1935, Einstein published a paper with two younger colleagues at the Institute for Advanced Study in Princeton, Boris Podolsky, who did most of the actual writing, and Nathan Rosen, a gifted theorist. The paper appeared in the Physical Review under the title, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It's now one of the most famous papers in the history of physics. Everyone calls it the EPR paper, after their initials. And the argument it made was beautifully, devastatingly simple. Here's the setup. Imagine you create two particles in a special way so that their properties are correlated. For example, you create two photons whose polarizations are linked. If you measure one and find it's polarized vertically, you know instantly that the other one is polarized horizontally. Every time, without fail. The correlation is perfect. You can also create pairs of particles with correlated spins. If one has spin up, the other has spin down. Or pairs with correlated positions and momenta. The details don't matter as much as the principle. The two particles are correlated, and the correlations are perfect. Now, according to quantum mechanics, neither particle has a definite property before you measure it. They're both in a superposition. But the moment you measure one and find it in a particular state, the other instantly becomes the corresponding state, even if it's on the other side of the universe. Einstein's argument was, how does the distant particle know what to become? If no signal can travel faster than light, then nothing you do to one particle can affect the other one instantaneously. And if your measurement doesn't send any signal, then the distant particle's state must have been determined all along. It was always going to be what it was. You just didn't know it until you measured its partner. The properties were set at the moment the particles were created, like writing the answers on two slips of paper. putting them in envelopes and sending them to opposite ends of the city. When you open your envelope, you learn what the other one says, but no information travels. The answers were always there. Therefore, Einstein concluded, quantum mechanics is incomplete. There must be some hidden variable, some additional piece of information that the theory doesn't capture, that determines the particle's properties from the start. The randomness and uncertainty of quantum mechanics aren't fundamental features of reality. They're just symptoms of our ignorance. Underneath, there's a deeper, deterministic reality. The particles know what they are. We just don't have a complete enough theory to describe it. This was the EPR argument, and it was a serious challenge. Einstein wasn't some crank. He was Einstein. His reasoning was clear and logical, and his conclusion that quantum mechanics is incomplete seemed perfectly reasonable. After all, the alternative was accepting that measuring a particle here could instantaneously affect a particle there, violating the spirit, if not the letter, of special relativity. Any reasonable person, Einstein felt, would prefer hidden variables to spooky action at a distance. Bohr responded almost immediately, and his response was, well, to be honest, it was confusing. Even physicists who supported Bohr found his counter-argument hard to follow. He didn't deny the correlations. He didn't deny that you could predict the distant particle's state by measuring the nearby one. What he argued, in his characteristically opaque and almost mystical style, was that you couldn't separate the two particles from the measurement process. The whole system, both particles and both measuring devices, was one quantum system, and you couldn't talk about the properties of one particle independently of how you chose to measure the other. The EPR argument assumed that you could assign definite properties to the distant particle based on what you measured locally. Bohr said this assumption was wrong, not because the physics was wrong, but because the very concept of the distant particle's property didn't have meaning until you specified the entire experimental context, including both measurements. If that sounds slippery, you're not alone. Many physicists at the time found Bohr's response unsatisfying. Even some who agreed with him in principle couldn't quite follow his reasoning. And Einstein remained unconvinced. The debate settled into a stalemate. Einstein and Bohr, the two giants of 20th century physics, disagreed fundamentally about the nature of reality, and neither could convince the other. They remained friends. Deep down, they respected each other enormously, but on this issue, they were immovable. For nearly 30 years, the question remained stuck, not because nobody cared, but because it seemed like a philosophical disagreement rather than a scientific one. Both sides agreed on the predictions of quantum mechanics. Both sides agreed on what the experiments would show. They just disagreed about what the results meant. And in physics, if two interpretations make the same predictions, there's no experiment that can tell them apart, or so everyone thought. Let's pause here for a moment and make sure we really understand what's at stake, because this isn't just an abstract philosophical question for professors to debate over coffee. It's a question about the fundamental nature of reality. Are the properties of particles real before we measure them? Or does reality only crystallize at the moment of observation? Is the universe deterministic at its core, with quantum randomness being just a cover for our ignorance? Or is the randomness fundamental, built into the structure of existence, irreducible, not a gap in our knowledge but a feature of the world? These are some of the deepest questions human beings have ever asked. And quantum mechanics, uniquely among scientific theories, has something concrete to say about them. Not speculation, not opinion, but hard experimental evidence. And that evidence came from an unlikely source, a quiet, unassuming Irish physicist working at CERN, the European Particle Physics Laboratory near Geneva, in the early 1960s. His name was John Stuart Bell, and what he did in 1964 might be the most important result in the history of quantum physics. Not the most famous. That honor probably goes to Einstein or Heisenberg or Schrödinger. But the most important, in terms of actually settling a question that had been open for 3 decades and that most people had given up on ever settling. Bell was an unusual physicist, and his story is worth dwelling on, because it's a reminder that great breakthroughs don't always come from the expected places. He was born in Belfast, Northern Ireland, in 1928, the son of a horse trader. He grew up in modest circumstances and showed an early talent for science, but his family couldn't afford to send him to university right away. He worked as a laboratory technician at Queen's University Belfast before eventually earning his degree. He was trained originally as an engineer and came to theoretical physics through a side door, so to speak. He ended up at CERN, the European Particle Physics Laboratory near Geneva, where he worked on designing particle accelerators, the giant machines that smash atoms together at nearly the speed of light. But accelerator design was his day job. In his spare time, evenings, weekends, sabbaticals, he thought about the foundations of quantum mechanics, and this was considered slightly eccentric, even a little embarrassing, by his colleagues. The prevailing attitude in physics at the time was captured by the phrase, "Shut up and calculate. Quantum mechanics works. The predictions match the experiments. Don't ask what it means. Don't waste time on philosophy. Just use the math and move on." Bell thought that attitude was intellectually lazy and scientifically wrong. He believed the foundational questions, the ones Einstein and Bohr had argued about, were real physics questions with real answers. And he kept asking them, even when nobody around him seemed interested. And the question he asked was deceptively simple. Is it possible to tell the difference between Einstein's view and Bohr's view? Remember, everyone assumed you couldn't. Both views made the same predictions. But Bell showed that this was wrong. He proved mathematically that if Einstein was right, if there were hidden variables determining particles' properties in advance, then there was a limit on how strongly correlated 2 entangled particles could be when measured at different angles. A mathematical ceiling, a boundary that no hidden variable theory, as long as it obeyed locality, could cross. And if quantum mechanics was right, if the particles genuinely didn't have definite properties until measurement, and the correlations were truly non-local, then that ceiling could be exceeded. The correlations could be stronger than anything a local hidden variable theory could explain. Let me try to make this more concrete, because it's a crucial point. Imagine Alice and Bob each have a detector, and they can set their detectors to measure the polarization of a photon along different angles. Alice can choose angle A or angle A prime. Bob can choose angle B or angle B prime. They each make their choice, measure their photon, and record whether it's polarized along their chosen axis or perpendicular to it. Then they compare results over many, many trials. What Bell showed was that if hidden variables determine the outcomes, then a certain combination of the correlations between Alice's and Bob's results, a specific mathematical expression involving the probabilities of their results agreeing or disagreeing for different angle choices, has to be less than or equal to a certain number. That's Bell's inequality. It's a ceiling, and any theory where the particles carry predetermined answers, any local hidden variable theory, must respect that ceiling. But quantum mechanics predicts that for certain carefully chosen angles, the correlations will exceed that ceiling. They'll be stronger than any predetermined answer scheme can produce. Not by a trivial amount either, by a significant, measurable amount. Bell expressed this precisely as an inequality, and he proved that quantum mechanics violates it. It's now called Bell's inequality, or more precisely, Bell's theorem. And the beauty of it was that it turned a philosophical question into an experimental one. You could actually go into a lab, create entangled particles, measure their correlations at various angles, and check whether Bell's inequality was satisfied or violated. Think about what that means. For 30 years, everyone assumed this was just philosophy, a question about interpretation, not about facts. Bell showed it was physics. He showed there was an actual, measurable difference between a universe with local hidden variables and a universe with genuine quantum entanglement. And he did it with a few pages of algebra that you could explain to a bright undergraduate. It's one of the most elegant, most consequential results in the history of science. But Bell's theorem was just theory. It told you what experiment to do. Someone still had to actually do it, and that took time, because the experiments were fiendishly difficult. You needed to create pairs of entangled particles, separate them, measure their properties at carefully chosen angles, and compare the results, all while making sure there was no way for the particles to communicate with each other, no hidden signal that could account for the correlations. Every possible loophole had to be considered and ideally closed. The first serious attempt came in 1972, when John Clauser and Stuart Friedman at the University of California, Berkeley, tested Bell's inequality using entangled photons produced by excited calcium atoms. Their results violated the inequality, siding with quantum mechanics. Clauser, by the way, was a graduate student at the time, and his advisor was not enthusiastic about the experiment. It was considered a fringe topic. But Clauser was stubborn. He believed the question was important, and he was right. The experiment worked. Bell's inequality was violated, but the experiment had loopholes. The measurement settings were fixed in advance, which meant that in principle, the particles could have known what measurement was coming and coordinated their responses accordingly. It sounds paranoid, almost conspiratorial. But in physics, if there's a loophole, you have to take it seriously. The definitive experiment came a decade later, in 1982, from a French physicist named Alain Aspect, working at the Institut d'Optique in Orsay, just south of Paris. Aspect's experiment was a masterpiece of experimental ingenuity. He used entangled photons, like Clauser, but with a crucial innovation. He changed the measurement settings while the photons were in flight. The settings were switched so fast, using acoustic optical switches that could flip in a few nanoseconds, that there was no way for a signal traveling at the speed of light to carry the information from one detector to the other in time. The photons were separated by about 12 meters, and the settings were changed in just tens of billionths of a second. Far too fast for any light-speed signal to cross the gap between the detectors. And the result? Bell's inequality was violated, spectacularly. The correlations between the entangled photons were exactly what quantum mechanics predicted, and stronger than any local hidden variable theory could explain. The universe did not work the way Einstein believed. The particles genuinely did not have definite properties until they were measured, and the correlations between them were genuinely non-local, spanning the gap between the two detectors without any signal passing between them. Einstein, had he lived to see it, would have been deeply troubled. He died on April 18, 1955, at the age of 76, at Princeton Hospital in New Jersey. On his deathbed, he was still working. There were pages of equations on his nightstand, part of his decades-long and ultimately unsuccessful attempt to find a unified field theory that would unite gravity and electromagnetism and, he hoped, replace quantum mechanics with something more sensible. He died 9 years before Bell's theorem and 27 years before Aspect's experiment. He never got to see the question settled. He never knew that the experiments would side against him. And there's something melancholy about that. The greatest physicist of the 20th century, perhaps of all time, dying without knowing the answer to the question that consumed his last 3 decades. But the answer was clear. Quantum mechanics was right. Entanglement was real, and the universe was stranger than Einstein was willing to believe. The spooky action at a distance that he had dismissed as absurd was exactly what nature was doing. And it had been doing it all along, in every entangled pair of particles, in every quantum interaction, throughout the entire history of the cosmos. Now, let's slow down and talk about what entanglement actually is, in more detail than the simple version we started with. Because the simple version, measure one particle and instantly know about the other, is true but incomplete. It doesn't capture what's really going on at the quantum level, and it can give you the wrong impression about what entanglement can and can't do. First, let's talk about quantum states. In quantum mechanics, every particle is described by something called a wave function, a mathematical object that contains all the information about the particle's possible states. For an electron, the wave function might tell you the probability of finding it at various positions, or the probability of its spin being up versus down. Spin, by the way, is a quantum property that's a bit like rotation, but not really. Electrons don't actually spin like tops, but they do have this intrinsic angular momentum that can point in one of 2 directions relative to any axis you choose. We call those directions up and down, but they're not literally up and down in space. They're just the 2 possible outcomes when you measure spin along a particular axis. When a particle is in a superposition, its wave function is a combination of multiple possible states. An electron's spin might be in a superposition of up and down, not spinning up, not spinning down, but in a kind of quantum blur that's genuinely both until you measure it. And this isn't a failure of language or a sign that we're confused. The math is precise. The superposition is a specific, well-defined mathematical state. It's just that this state doesn't correspond to any familiar classical picture. When you do measure it, you get one or the other, up or down, with probabilities determined by the wave function. And after the measurement, the particle is in a definite state. The superposition has collapsed, as they say. Now, entanglement is what happens when 2 particles' wave functions become linked, intertwined in a way that means you can't describe one particle's state independently of the others. Normally, if you have 2 particles, each one has its own wave function, its own quantum state. The combined system is just the 2 individual states stuck together, like 2 separate files in a folder. But when 2 particles are entangled, their combined state can't be broken apart like that. They share a single wave function. The state of the pair is one thing, not 2 separate things. And this shared state has a peculiar property. It contains correlations between the particles' possible measurement outcomes, but it doesn't assign definite properties to either particle individually. Let me make that concrete. Say you have 2 entangled electrons prepared so that their spins are correlated. If one is up, the other is down, and vice versa. The total spin of the pair is 0, because up and down cancel out. This is called a singlet state, and it's one of the most studied entangled states in physics. Now, before you measure either electron, neither one has a definite spin. They're both in a superposition of up and down, but the superposition is correlated. It's not that each electron is independently maybe up, maybe down. It's that the pair is in a state where the 2 spins are always opposite, but neither one is determined until a measurement is made. Here's an analogy that might help, though like all analogies for quantum mechanics, it's imperfect. Imagine a pair of magic gloves, one left-handed, one right-handed, in a box. You close your eyes, grab one, and mail the other to your friend in another city. When you open the box and find a left glove, you instantly know your friend has the right glove. No mystery there. But the quantum version is different. In the quantum version, before you open the box, The glove genuinely isn't left or right. It's in a superposition of both, a left-right blur. And the moment you look and find a left glove, your friend's glove, which also wasn't left or right, instantly becomes a right glove, even if your friend is on Mars. Now, this analogy breaks down in an important way, and I want to be honest about that, because the places where analogies break are where the real understanding lives. The glove analogy makes it sound like the gloves become left and right because of some predetermined rule, like they were always going to be that way, and you just didn't know. That's exactly what Einstein believed. Bell's theorem shows that this can't be the full story. The correlations in quantum entanglement, when you measure at different angles, are stronger than any predetermined answer scheme can explain. The particles really aren't decided in advance. The quantum state is genuinely indeterminate until measurement, and the correlations are genuinely non-local. So how do you create entangled particles in the first place? There are several methods, and they all involve some process that conserves a quantum number. The most common approach for photons is called spontaneous parametric down conversion. You shoot a high-energy photon, usually ultraviolet, into a special kind of crystal called a nonlinear crystal, and the crystal splits it into two lower-energy photons, usually in the visible or infrared range. These two daughter photons emerge entangled. Their polarizations are correlated because of conservation laws. The total polarization, momentum, and energy have to be conserved, so the two photons' properties are linked by those conservation rules. And because quantum mechanics doesn't assign definite properties until measurement, those linked properties remain in a superposition, in an entangled state, until someone measures one of them. For electrons, you can use quantum dots, or certain atomic decays that produce pairs of electrons with correlated spins. For atoms, you can entangle them using careful laser manipulations and electromagnetic traps. The details vary, but the principle is always the same. You use a physical process that creates a pair of particles whose properties are linked by conservation laws, and the entanglement naturally falls out of the quantum mechanical description. Now, there's a question you might be asking at this point, and it's a really good one. A really natural, important, obvious question. If measuring one entangled particle instantly affects the other, no matter how far apart they are, doesn't that mean you can send messages faster than light? Couldn't you use entanglement as a kind of quantum telephone? Encode a message in one particle and have it appear instantly at the other end? The answer is no. And this is one of the most important and most misunderstood aspects of entanglement. So let's take our time with it. When you measure your entangled particle, you get a random result. Spin up or spin down, vertical or horizontal polarization. Whatever you're measuring, the outcome is genuinely random. You can't control it. You can't choose to get up instead of down. So you can't encode a message in your measurement outcome. You don't get to choose the outcome. Your result is just a random bit, sometimes 0, sometimes 1, with no pattern and no information content. Your distant partner also measures their particle and gets a random result. And if you later compare your results by phone, by email, by carrier pigeon, by some method that necessarily obeys the speed of light, you'll find that your results are perfectly correlated. When you got up, they got down. When you got horizontal, they got vertical. The correlations are real. But neither of you, looking at your own results in isolation, can tell anything unusual is happening. Your results look random. Their results look random, completely random. It's only when you bring the two sets of results together and compare them side by side that the correlations become visible, and that comparison requires ordinary, speed-of-light communication. So no faster-than-light messaging, no instantaneous quantum telephone. The correlations are there, but they're hidden in the noise of individually random measurements. It's as if the universe conspires to maintain the speed of light limit, allowing these spooky correlations to exist, but never allowing them to carry usable information faster than light. Physicists call this the no-signaling theorem, and it's been proved rigorously. Quantum entanglement, for all its strangeness, cannot be used to transmit information faster than light. The speed of light barrier holds. This is actually a deep and subtle point that's worth sitting with. Entanglement is non-local. The correlations don't respect distance. But the non-locality is of a very specific kind that doesn't allow faster-than-light signaling. Physicists sometimes say that entanglement involves non-local correlations without non-local communication. The correlations are real, but they can't be exploited to send messages. It's as if nature draws a careful line. You can have correlations that transcend space, but you can't use them as a telephone. The universe is non-local in its correlations, but local in its information transfer. That's a distinction that seems almost designed to frustrate anyone trying to build a faster-than-light communicator. Einstein would have found this both reassuring and maddening. Reassuring because the speed of light is preserved. No information travels faster than light, just as his theory of relativity demands. Maddening because the correlations are still there, still non-local, still defying any explanation in terms of signals or influences. The universe seems to go out of its way to maintain the correlations while preventing them from being useful for signaling. It's as if nature is saying, "Yes, I know this looks like I'm violating your rules, Albert, but technically I'm not. I'm just being really, really weird within the letter of the law." Let's talk about what happened after Aspect's experiment, because 1982 was the breakthrough, but it wasn't the end of the story. Not even close. Over the following decades, experimentalists kept testing Bell's inequality with greater and greater precision, pushing the particles farther apart, closing loopholes one by one, and exploring entanglement in systems that the original experimenters never dreamed of. In 1998, a team in Geneva, Switzerland, led by Nicolas Guissin, tested entangled photons separated by more than 10 kilometers using the existing fiber optic telecommunications network running under the city. They sent one photon to a lab in Bellevue and the other to a lab in Bernex, on opposite sides of Geneva, and measured their correlations. Bell's inequality was violated. The correlations held perfectly over 10 kilometers of fiber optic cable. In 2008, Anton Zeilinger's group in Vienna tested entangled photons separated by 144 kilometers, sent through the open air between two of the Canary Islands, La Palma and Tenerife. The photons traveled through the atmosphere, through turbulence and humidity and all the disturbances of the real world, across a stretch of open ocean, and Bell's inequality was still violated. The correlations were still there, undimmed by distance. And in 2017, a Chinese satellite called Mikius, named after the ancient Chinese philosopher Mo Tzu, distributed entangled photons between ground stations separated by 1,200 kilometers. The satellite created the entangled pairs in orbit and sent one photon down to each station, which were in different Chinese cities. And Bell's inequality was violated at that distance too, 1,200 kilometers. Think about that for a moment. Two photons, born together from a crystal in orbit, sent to opposite ends of a country, and when you measure one, the other responds, instantly, across a distance that light itself needs about 4 milliseconds to cross. But these experiments weren't just about distance. They were also about closing loopholes, the subtle possibilities that critics had identified as potential escape routes for hidden variable theories. There were three main loopholes that needed to be addressed: the locality loophole, the detection loophole, and the freedom of choice loophole. Each one represented a way that the correlations could, in principle, be explained without genuine non-locality. The locality loophole is the one aspect addressed, making sure the measurement settings are chosen so fast that no signal could travel between the detectors in time. If the detectors are close together and the settings are chosen slowly, you could imagine a hidden signal traveling from one to the other, coordinating the results like two students passing answers during an exam. Aspect closed this by switching settings while the photons were in flight. The detection loophole is more subtle. In many experiments, not every photon is actually detected. Some are lost in transit, absorbed by the equipment, or simply miss the detector. If the undetected photons are systematically different from the detected ones, if the missing photons are precisely the ones that would have broken the correlation, then the results are biased. You'd be seeing stronger correlations just because the non-conforming photons are invisible. To close this loophole, you need detectors efficient enough to catch nearly every particle. The freedom of choice loophole is perhaps the most philosophically interesting. It asks, what if the measurement settings aren't truly random? What if there's some subtle influence, some common cause in the distant past, perhaps at the Big Bang itself, that correlates the choice of measurement settings with the particles' hidden variables? In that case, the particles could know what's going to be measured and adjust their responses accordingly, without any non-local influence needed. This loophole is sometimes called superdeterminism, and it's extremely hard to close completely. But some experiments have addressed it by using astronomical random number generators, using the light from distant quasars, billions of light-years away, to determine the measurement settings. The idea is that these distant photons were emitted long before the experiment, long before the entangled particles were created, making it essentially impossible for any common cause to have correlated them. In 2015, 3 separate groups performed what are called loophole-free Bell tests, experiments that closed all 3 major loopholes simultaneously. The most prominent was led by Ronald Hansen at the Delft University of Technology in the Netherlands. Hansen's team used entangled electrons in diamond defects, nitrogen vacancy centers, which are atomic-scale imperfections in diamond crystals that behave like little quantum systems, separated by 1.3 kilometers across the Delft campus. The measurement settings were chosen by fast random number generators, and the detectors were efficient enough to close the detection loophole. The experiment was extraordinarily difficult. It took years of painstaking preparation, but the result was clear. Bell's inequality was violated, with all 3 major loopholes closed simultaneously. Quantum mechanics won again. There was simply no room left for local hidden variables. Let's take a breath here and think about what all of this means. It's easy to get lost in the technical details, the inequality, the loopholes, the experimental setups, and miss the forest for the trees. So let's step back. What these experiments have shown with extraordinary precision and rigor, accumulated over more than 4 decades of testing, is that the universe does not work the way Einstein believed. There are no local hidden variables. Particles genuinely do not have definite properties before you measure them, and entangled particles are genuinely connected in a way that transcends the normal limitations of space. Now, I want to add an important nuance here, because I said local hidden variables. That qualifier matters. Bell's theorem rules out local hidden variable theories, theories where the hidden variables are associated with each particle individually and where influences between particles are limited by the speed of light. It's technically possible to construct non-local hidden variable theories, theories where the hidden variables can influence each other faster than light. David Bohm, a brilliant American-born physicist who spent much of his career in exile in Brazil and Britain due to Cold War politics, proposed such a theory in 1952. In Bohm's theory, called Bohmian mechanics or pilot wave theory, particles have definite positions at all times, like classical particles, but they're guided by a pilot wave that permeates all of space and can carry influences instantaneously. It reproduces all the predictions of quantum mechanics, including the violation of Bell's inequality, because the pilot wave is explicitly non-local. Most physicists find Bohm's theory unattractive, not because it's wrong. It makes all the same predictions as standard quantum mechanics, but because the non-local pilot wave feels ad hoc. You're saving determinism, but at the cost of introducing an invisible, faster-than-light influence that you can never directly detect. To many, that's trading one kind of weirdness for another, and the second kind doesn't seem obviously better. But Bohm's theory exists, it's consistent, and the fact that it's viable tells you something important. We still don't have a consensus on what quantum mechanics actually means. We know the math, we know the predictions, we can do the experiments. But the question of what is really happening, what reality looks like between measurements, remains open. And this brings us to the interpretation question, which I think is worth exploring, because it's where physics and philosophy meet in a way that's unusually intimate. In most branches of science, the interpretation of a theory is obvious. When biologists talk about evolution by natural selection, everyone agrees on what it means. The mechanism is clear. The ontology, what actually exists and what's happening, is not really in dispute. Quantum mechanics is profoundly different. The math is unambiguous. The predictions are precise and confirmed to extraordinary accuracy. But what the math describes, what kind of world it's telling us about, is genuinely unclear. The Copenhagen interpretation, which we've already talked about, says that the wave function isn't a real thing. It's a mathematical tool for calculating probabilities. The act of measurement causes the wave function to collapse, and it doesn't make sense to ask what the particle was doing before you measured it. There's no underlying reality beneath the quantum description. The many worlds interpretation, proposed by Hugh Everett in 1957 when he was a graduate student at Princeton, just 2 years after Einstein died there, which feels like a cosmic passing of the torch, says something much more dramatic. In this view, the wave function never collapses. Instead, every possible outcome of every measurement actually occurs, in separate branches of a vast, constantly splitting multiverse. When you measure an electron's spin and get up, there's another branch of the universe where you got down. Both outcomes are equally real. Both versions of you are equally real. You just happen to be the version who got up. In the many worlds view, entanglement looks a little different. When you measure one entangled particle, the universe branches. In one branch, you got up, and your partner got down. In another branch, you got down, and your partner got up. There's no spooky action at a distance, because there's no collapse. The wave function just keeps evolving according to Schrödinger's equation, branching but never collapsing. The correlations are preserved because the branching is global. It affects both you and your partner simultaneously. The non-locality is, in a sense, absorbed into the branching structure of the multiverse. Then there's the relational interpretation, proposed by the Italian physicist Carlo Rovelli, which says that quantum states aren't properties of particles in isolation. They're relations between a particle and an observer. My description of a particle is relative to me. Your description of the same particle is relative to you. And these descriptions don't have to agree until we interact and compare notes. In this view, there's no absolute quantum state, no view from nowhere, just a web of relations between physical systems. And there's cubism, quantum Bayesianism, which treats the wave function as a representation of an agent's personal beliefs about what they'll experience next. In cubism, quantum mechanics isn't about the world out there. It's about the interface between an agent and the world. The wave function is like a weather forecast. It tells you the probabilities, but the probabilities are your probabilities, based on your information, not a feature of the weather itself. Each of these interpretations handles entanglement differently. Each one is consistent with all the experiments, and each one offers a different answer to the question, what is really happening? The fact that we have multiple viable answers and no experimental way to distinguish between them is either a deep insight about the limits of physics or a temporary embarrassment that will be resolved by some future breakthrough, depending on who you ask. Now, before we move on to the practical side of entanglement, I want to take a detour through one of the most famous thought experiments in all of physics, because it's directly connected to entanglement in ways that people don't always realize. I'm talking about Schrödinger's cat. You probably know the basic setup. Schrödinger proposed it in 1935, the same year as the EPR paper, the same year he coined the word entanglement. It wasn't a coincidence. He was responding to the EPR argument, thinking through its implications, and he came up with the cat to illustrate just how strange those implications were. Here's the idea. You put a cat in a sealed box with a tiny bit of radioactive material, a Geiger counter, and a vial of poison. If a radioactive atom decays within the next hour, the Geiger counter detects it, triggers a mechanism that breaks the vial, and the poison kills the cat. If no atom decays, the cat lives. Now, according to quantum mechanics, the radioactive atom is in a superposition of decayed and not decayed until someone observes it. And if the atom is in a superposition, then the entire chain of events, decay, Geiger counter, vial, cat, is also in a superposition. The cat, says the strict quantum formalism, is in a superposition of alive and dead, not alive or dead, not alive and we don't know which, alive and dead, simultaneously. Schrödinger didn't propose this because he believed it. He proposed it because he thought it was absurd. He was trying to show that the Copenhagen interpretation, taken to its logical conclusion, led to ridiculous results. A cat can't be alive and dead at the same time. That's not how the world works. Therefore, Schrödinger argued, something must be wrong with the interpretation, or at least, something must be missing. But here's the connection to entanglement that often gets missed. The cat thought experiment is really an entanglement scenario in disguise. The radioactive atom becomes entangled with the Geiger counter, which becomes entangled with the vial, which becomes entangled with the cat. Each link in the chain gets drawn into the entangled state. The atom and the cat are entangled. If the atom decayed, the cat is dead. If it didn't, the cat is alive. The correlations are perfect, just like with two entangled photons. The difference is scale. We're used to thinking of entanglement as something that happens to tiny particles in a lab. Schrödinger's thought experiment asks, why should it stop there? If entanglement is a fundamental feature of quantum mechanics, why doesn't it scale up to cats, to people, to everything? And here's where it gets really interesting. In principle, it does scale up. There's nothing in the equations of quantum mechanics that says superposition and entanglement only apply to small things. The math doesn't have a size limit. A cat, a person, a planet, they're all quantum systems, described by wave functions, capable in principle of existing in superpositions and becoming entangled with other systems. So why don't we see quantum effects at the everyday scale? Why don't we see cats that are alive and dead simultaneously? Why does the macroscopic world look so classical, so definite, so unsuperposed? The answer, or at least the best answer we currently have, is a process called decoherence. And understanding decoherence is essential to understanding why entanglement seems so exotic and fragile. even though the math says it should be everywhere. It's one of the most important ideas in modern quantum physics, and it was only fully developed in the 1970s and 1980s, primarily through the work of the German physicist H. Dieter Zeh and the Polish-American physicist Wojciech Zurek. For decades after quantum mechanics was formulated, nobody had a clear explanation for why the quantum world looked classical at large scales. Decoherence provided that explanation, and it changed how physicists think about the boundary between quantum and classical. So what is decoherence? It's what happens when a quantum system interacts with its environment. And by environment, I mean everything around it. Air molecules, stray photons, vibrations in the walls, thermal radiation, cosmic rays, the whole buzzing, jostling, chaotic world of macroscopic matter. When a quantum system is perfectly isolated, like a single photon traveling through a vacuum, or an electron in a carefully controlled lab setup, its quantum properties are preserved. Superpositions remain superpositions. Entanglement stays intact. But the moment the system starts interacting with the environment, something happens. The quantum information leaks into the environment. The superposition doesn't exactly disappear. In a very technical sense, the system becomes entangled with the environment. But this entanglement with a vast, complicated, uncontrollable environment means that the delicate quantum coherence, the thing that makes superposition and entanglement work, gets smeared out across so many environmental particles that it becomes effectively invisible. Think of it this way. Imagine you're in a concert hall, and a single violin plays a clear, pure note. You can hear it perfectly. Now imagine 1,000 instruments start playing random notes at the same time. The violin is still playing. Its sound waves are still there, but they're drowned out by the noise. You can't pick out the violin anymore. That's roughly what decoherence does to quantum superpositions. The quantum information isn't destroyed, but it's overwhelmed by interactions with the environment. It becomes inaccessible. For all practical purposes, the superposition is gone, and the system behaves classically. And here's the key fact. Decoherence happens incredibly fast for large objects. For a single photon in a vacuum, quantum coherence can be maintained indefinitely. For an electron in a lab, it can last microseconds, or even longer, with careful shielding. But for something the size of a cat, decoherence would happen in a fraction of a trillionth of a second. The cat's superposition would dissolve almost instantaneously into classical definiteness. The environment would measure the cat long before any human observer got a chance to open the box. This is why the quantum world looks classical to us. Not because quantum mechanics stops applying at some magic size, but because large objects interact with their environments so intensely and so constantly that their quantum properties are immediately washed out. The classical world we see around us is quantum mechanics, averaged over an enormous number of environmental interactions. It's what quantum mechanics looks like when decoherence has done its work. And this has direct implications for entanglement. Creating and maintaining entanglement between particles is hard, precisely because of decoherence. The entangled particles need to be isolated from their environment, shielded from stray photons, cooled to near absolute zero, suspended in magnetic traps. Any interaction with the outside world can destroy the entanglement. That's why quantum computing is so difficult to build. You need to maintain entanglement between many qubits simultaneously, and decoherence is constantly trying to tear it apart. It's like trying to balance thousands of spinning plates while someone shakes the table. But there's a flip side to this story that's quite remarkable. Despite how fragile entanglement is, despite the constant threat of decoherence, nature produces entanglement constantly and effortlessly. Every interaction between particles involves a kind of entanglement. When a photon bounces off a mirror, the photon and the mirror become briefly entangled. When you touch a table, the electrons in your fingers and the electrons in the table become entangled at the point of contact. Entanglement is everywhere. It's happening right now, in your body, in the air you're breathing, in the bed you're lying on. The universe is a vast web of entanglement, constantly being created and constantly being dissolved by decoherence. What we do in the lab, when we carefully create entangled pairs of photons or electrons, is just a tiny, controlled version of something that nature does everywhere, all the time, without any effort at all. There's something poetic about that, I think. The quantum world isn't separate from the everyday world. It's underneath it. Entanglement isn't exotic. It's the most common thing in the universe. What's exotic is isolating it, controlling it, preserving it long enough to study it and use it. The strangeness isn't in the particles. It's in the fact that we manage to see it at all. Let me tell you about one more fascinating aspect of entanglement before we move to its practical applications. And that's the question of how far you can push it, not just in distance, but in terms of what kinds of systems you can entangle. Because it's not just photons and electrons. Over the past couple of decades, physicists have entangled atoms, ions, molecules, and even macroscopic objects. In 2011, researchers at the University of Oxford entangled 2 diamond crystals, each about 3 millimeters across, visible to the naked eye. They used ultra-fast laser pulses to create a state where a single quantum of vibration, called a phonon, was shared between the 2 crystals. The phonon existed in both crystals simultaneously, in a superposition, just like a photon in a 2-slit experiment. This was the first demonstration of entanglement between macroscopic objects that you could actually see and hold. 3 millimeters might not sound like much, but compared to the subatomic particles where entanglement was first observed, it's absolutely enormous. Billions of atoms, all participating in a single quantum state. More recently, physicists have entangled mechanical oscillators, tiny drumheads that vibrate at quantum frequencies. In 2018, a team at the National Institute of Standards and Technology managed to entangle the vibrations of 2 aluminum membranes, each about the size of a human hair, showing that even the mechanical motion of physical objects can exhibit quantum entanglement. The quantum world isn't shrinking into irrelevance as things get bigger. It's reaching up, making itself felt at larger and larger scales. We just need clever enough experiments to see it. There's also the tantalizing question of entanglement in biological systems. Some researchers have proposed that quantum effects, including entanglement, might play a role in photosynthesis, the process by which plants convert sunlight into energy. The idea is that the quantum coherence of excitation energy in chloroplasts might help plants transfer energy with remarkable efficiency, finding the best pathway through a complex molecular network faster than any classical process could. This is still hotly debated, and the evidence is mixed. But if it's true, it would mean that life itself has been harnessing quantum entanglement for billions of years, long before any physicist figured out what it was. Evolution, it seems, might have been a quantum engineer all along. Another area where entanglement might play a role is in the navigation systems of certain birds. European robins, for instance, seem to sense the Earth's magnetic field for navigation, and one leading hypothesis involves a quantum process in molecules in their eyes called cryptochrome. The idea is that pairs of electrons in these molecules become entangled, and their entangled state is sensitive to the magnetic field. The bird's visual system then reads the state of these entangled pairs and uses the information to determine direction. If this is right, and it's still an if, then a robin navigating from Scandinavia to Africa is literally using quantum entanglement as a compass. That's a thought that would have made Einstein's head spin. But let's bring this back to something even more concrete. Because while the interpretation question and the biological speculations are endlessly fascinating, entanglement isn't just a philosophical curiosity or a biological hypothesis. It's a resource, a tool, something we can actually build things with. And over the past few decades, physicists and engineers have figured out how to harness it for technologies that would be flat out impossible without it. The most famous application is quantum computing. You've probably heard of quantum computers. They're in the news a lot, often surrounded by a lot of hype and not always a lot of clarity. So let's talk about what they actually are and how entanglement makes them work. A classical computer stores information in bits, zeros and ones, like tiny switches that are either on or off. Everything your phone or laptop does is ultimately built from those two states. A quantum computer uses quantum bits, or qubits, which can exist in a superposition of 0 and 1 simultaneously. That's interesting, but superposition alone doesn't give you a quantum computer. Lots of quantum systems have superposition. The real power comes from entanglement. When qubits are entangled, they can process information in ways that classical bits fundamentally can't. The entanglement creates correlations between the qubits that enable certain computations to be performed exponentially faster than any classical computer could manage. Take factoring large numbers, for example. If I give you a number with 600 digits and ask you to find its prime factors, a classical computer would need longer than the current age of the universe to solve it using any known algorithm. But a quantum computer running Shor's algorithm, developed by the mathematician Peter Shor at Bell Labs in 1994, could do it in a matter of hours. This isn't just theoretically interesting, it's a practical concern, because the security of most internet encryption relies on the assumption that factoring large numbers is practically impossible. Every time you buy something online, every time you send an encrypted message, the security is built on the difficulty of factoring very large numbers. A large enough quantum computer would break that encryption completely. We don't have such a quantum computer yet. As of now, quantum computers are still in their early stages, noisy, error-prone, with at most a few thousand qubits that are fiendishly difficult to keep coherent. You need millions of high-quality, error-corrected qubits to run Shor's algorithm on a number large enough to threaten real-world encryption. But the field is advancing steadily, with major efforts underway at Google, IBM, and dozens of universities and startups around the world. And the theoretical framework is clear. Entanglement is the key ingredient that makes quantum computing fundamentally more powerful than classical computing. Without entanglement, a quantum computer is just a fancy random number generator. There's a beautiful way to think about why entanglement makes quantum computing so powerful. In a classical computer with, say, 300 bits, you can represent one number at a time, one specific arrangement of zeros and ones. But 300 entangled qubits can, in a sense, explore 2 to the power of 300 states simultaneously. That's a number so large, it exceeds the number of atoms in the observable universe by an incomprehensible margin. Entanglement allows the qubits to coordinate their exploration of this vast space of possibilities, interfering constructively where the right answers are and destructively where the wrong answers are until the solution emerges. It's not quite parallel computing in the classical sense, but it's something equally powerful and far stranger. Then there's quantum teleportation, and I need to be very careful here, because the word teleportation is misleading and gets people excited for the wrong reasons. Quantum teleportation does not involve transporting matter from one place to another. You're not beaming atoms across space. What you're transporting is a quantum state, the complete quantum description of a particle, from one location to another, using entanglement and classical communication working together. Here's how it works, roughly. Alice has a particle in some unknown quantum state that she wants to send to Bob. She can't simply measure the state and tell Bob, because measuring it would destroy the superposition. She'd get one random outcome and lose all the rest of the information. She also can't copy the state because of the no-cloning theorem, a fundamental quantum principle that says you cannot make a perfect copy of an unknown quantum state. So what does she do? Alice and Bob each hold one particle from a shared entangled pair. Alice performs a special joint measurement on her original particle and her half of the entangled pair. This measurement gives her a random result, 2 bits of classical information. She sends those 2 bits to Bob over an ordinary channel. Bob then uses those 2 bits to perform a specific operation on his half of the entangled pair, and, remarkably, his particle ends up in exactly the same quantum state that Alice's original particle was in. The state has been teleported. Notice what happened. No matter moved. No particle traveled from Alice to Bob. The state was transmitted using a combination of pre-shared entanglement and classical communication. The teleportation still requires a classical signal, which obeys the speed of light, so it's not faster than light communication. But the result is remarkable. A quantum state has been faithfully reproduced at a distant location, even though quantum mechanics forbids measuring or copying that state. Teleportation gets around the no-cloning theorem by destroying the original. The state isn't copied, it's moved. Quantum teleportation was first demonstrated experimentally in 1997, independently by 2 groups, one led by Anton Zeilinger in Innsbruck, Austria, and the other by Francesco de Martini in Rome. Since then, it's been demonstrated over increasing distances, and the Chinese Mikius satellite demonstrated teleportation from a ground station to orbit, the first time a quantum state was teleported into space. The practical importance is for future quantum networks, where entanglement and teleportation will serve as the backbone for transmitting quantum information between distant quantum computers. Another powerful application is quantum key distribution, quantum cryptography, for generating unbreakable encryption keys. Alice and Bob share entangled particle pairs and measure them to generate matching random strings of bits. Because of quantum mechanics, any eavesdropper who intercepts and measures the particles will disturb the entanglement, introducing detectable errors. The laws of physics themselves guarantee the security. If the error rate stays below a certain threshold, Alice and Bob know nobody has eavesdropped, and they can use their shared key to encrypt messages with absolute security. This technology is already being deployed. China has built quantum communication networks spanning thousands of kilometers, and European projects are underway to do the same. There's also quantum sensing, using entanglement to make measurements more precise than classical physics allows. The basic idea is that entangled particles can be correlated so tightly that the noise in their measurements partially cancels out. If you're trying to measure a tiny magnetic field, or detect a faint gravitational wave, or image a biological molecule with atomic precision, entangled particles can give you a sensitivity boost that no classical measurement technique can match. This isn't science fiction. Quantum sensors are being developed right now for medical imaging, geological surveying, and navigation systems that work without GPS. The same spooky correlations that troubled Einstein are being turned into instruments of exquisite precision. And there's something quietly profound about all of these applications. Entanglement started as an argument against quantum mechanics, a thought experiment designed to show that the theory was incomplete. And now, less than a century later, it's the basis of entirely new technologies. The thing Einstein thought was a bug turned out to be one of the most powerful features of quantum mechanics. That's a trajectory that says something important about the relationship between fundamental science and practical applications. The most abstract, the most philosophical, the most seemingly useless questions in physics have a way of becoming, decades later, the foundations of transformative technologies. Einstein couldn't have imagined quantum computing or quantum teleportation, but by asking the right questions about entanglement, he helped set in motion the chain of ideas that made them possible. But maybe the most mind-bending connection involving entanglement is its potential link to the structure of space-time itself. Now, I want to be very clear. This is cutting-edge theoretical physics. Speculative, not experimentally confirmed. But it's so fascinating and so suggestive of where physics might be heading that it's worth exploring, with the understanding that we're leaving solid ground and entering the realm of educated conjecture. In 2013, two theoretical physicists, Juan Maldacena, an Argentine-American physicist at the Institute for Advanced Study in Princeton, and Leonard Susskind at Stanford, proposed a conjecture that has become known as ER equals EPR. The ER stands for Einstein-Rosen bridges, better known as wormholes, hypothetical tunnels through space-time connecting two distant regions, which Einstein and Rosen described in a paper in 1935. And EPR stands for the entanglement described in the Einstein-Podolsky-Rosen paper of the same year. Two papers, same year, same first author. And Maldacena and Susskind proposed that these two things, wormholes and entanglement, are actually the same phenomenon, seen from different angles. If this conjecture is correct, and it's a big if, then every pair of entangled particles is connected by a tiny, microscopic wormhole. Not a traversable wormhole, not one you could send anything through, but a geometric connection in the fabric of space-time itself. And conversely, every wormhole is a kind of entanglement between the regions of space-time it connects. Entanglement isn't just a feature of quantum mechanics, it's a feature of space-time. The very fabric of space might be stitched together by entanglement. Take away the entanglement, and space falls apart. The threads that hold the universe together aren't made of matter or energy or force. They're made of quantum correlations. Think about that for a moment. The space between you and the wall across the room might exist because of entanglement. The distance between the Earth and the Moon might be a consequence of quantum correlations. Space itself might not be the fundamental thing. Entanglement might be. And space, distance, geometry, all the things that seem most basic and obvious about the physical world, might emerge from something deeper, something quantum, something that Einstein spent his whole life resisting. There's a delicious irony here, and it's one I keep coming back to. Einstein's two great contributions, general relativity, which describes the geometry of space-time, and the EPR argument about entanglement, might turn out to be two aspects of the same thing. The thing he used to argue against quantum mechanics might be the key to unifying quantum mechanics with his own theory of gravity. If ER equals EPR, then Einstein's objection to entanglement was actually a clue to the deepest structure of reality. He was right to think entanglement was important. He was right to sense that it pointed to something fundamental. He was just wrong about what that something was. But I want to be careful, because this is speculative physics. The ER equals EPR conjecture hasn't been proved, and it might turn out to be wrong or only partially right. It's part of a broader research program in theoretical physics, connected to string theory, the ADS-CFT correspondence, and the study of quantum gravity, that is still very much a work in progress. Some of the brightest minds in physics are working on it, and they disagree with each other about many of the details. That's how science works at the frontier. Ideas are proposed, debated, tested, refined, sometimes abandoned. We won't know for years, maybe decades, whether this picture is right. But the fact that entanglement might underlie the geometry of space-time itself tells you how far we've come from Einstein's dismissive, spooky action at a distance. Entanglement has gone from an embarrassment to perhaps the most important concept in all of fundamental physics. Let me circle back now to Einstein, because I think his story deserves more nuance than the simple version, "He was wrong about entanglement," suggests. Yes, Einstein was wrong about the specific question of whether local hidden variables could explain entanglement. Bell's theorem and the subsequent experiments proved that conclusively. But Einstein's broader concerns, his insistence that physics should describe an objective reality, his discomfort with a theory that only predicts probabilities, his conviction that quantum mechanics was incomplete, those concerns haven't gone away. They're at the heart of the interpretation debate that continues to this day. Every physicist who works on quantum foundations is, in some sense, grappling with Einstein's questions. And Einstein's instinct that something was deeply important about entanglement, that it pointed to something fundamental about the nature of reality, was absolutely correct. He just thought it pointed toward hidden variables. It actually pointed toward something far stranger, the non-local, interconnected fabric of reality itself. Einstein's mistake wasn't that he took entanglement too seriously. It's that he didn't take it seriously enough. He saw it as a problem to be solved, a bug to be fixed. It turned out to be a window into the deepest structure of the universe. Schrödinger, the same Schrödinger who gave us the famous cat, actually coined the word entanglement in 1935, the same year as the EPR paper. He called it Verschränkung in German, which means something like interlocking or intertwining, and he recognized, even then, that it wasn't just a feature of quantum mechanics. It was the feature, the one that made quantum mechanics genuinely different from anything that came before. He wrote that he would not call it one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Schrödinger understood, nearly 90 years ago, that entanglement was the heart of the quantum mystery. Let me tell you one more story before we start to wind down. It's about the Nobel Prize in 2022, which was awarded to 3 physicists, Alain Aspect, John Clauser, and Anton Zeilinger. 3 men who, over the course of nearly 50 years, turned entanglement from a philosophical curiosity into an experimentally confirmed phenomenon and a practical technology. Clauser, the stubborn graduate student who did the first real test. Aspect, the meticulous French experimentalist who closed the first major loophole. And Zeilinger, the visionary Austrian who pushed entanglement to its limits, teleporting quantum states, beaming entangled photons through the atmosphere, working with satellites, and helping to lay the groundwork for a future quantum internet. When the Nobel Committee announced the 2022 prize, they described the laureate's work as having established that Bell inequalities are violated in the real world, confirming the predictions of quantum mechanics and opening the door to new quantum technologies. But behind that dry language was a story of decades of persistence, often against the prevailing winds of the physics community. Clauser was initially turned down for funding. Aspect was told his experiment was a waste of time. Zeilinger was considered a little bit of a dreamer, more interested in philosophy than real physics. All 3 men persisted because they believed the question was too important to leave unanswered. And they were right. During his Nobel lecture, Zeilinger described the moment he first understood Bell's theorem as a feeling of vertigo. The ground shifted under his feet. Because if Bell was right, if the experiments could really distinguish between hidden variables and quantum mechanics, then the question of what reality is was no longer just philosophy. It was experimental physics. You could go into a lab and find out something about the ultimate nature of reality. And that realization shaped the rest of his career. He spent the next 4 decades doing exactly that, going into labs and finding out, pushing entanglement farther, testing it harder, using it for things nobody had thought possible. And now, in his 70s, he stood on a stage in Stockholm and told the world what he and his colleagues had learned, that the universe really is as strange as quantum mechanics says it is, maybe stranger. So where does that leave us? We started with a simple question. What is quantum entanglement, and why did Einstein refuse to believe it? And we've traveled a long way, through the birth of quantum mechanics at the dawn of the 20th century, through Einstein's own contributions to the theory he would later fight against, through the fierce debates between Einstein and Bohr at the Solvay conferences, through the brilliant EPR argument and Bohr's muddled response, through the quiet genius of John Bell and the painstaking experiments of Clauser, Aspect, and Zeilinger, through the interpretations and the applications and the breathtaking possibility that entanglement might be woven into the very fabric of space-time itself. And the answer to our question is both simpler and stranger than you might have expected. Quantum entanglement is what happens when 2 particles become so deeply correlated that they can no longer be described independently. Their quantum states are intertwined, not by any physical connection, not by any signal traveling between them, but by the mathematics of quantum mechanics itself. When you measure one, you learn about the other, instantly, regardless of distance. And this isn't because the particles were secretly carrying the answers all along, like coins in envelopes. The experiments have shown, beyond any reasonable doubt, that the answers don't exist until the measurement is made. The universe makes it up on the spot, and somehow it makes it up consistently, with perfect correlations, across any distance you care to test. Einstein refused to believe it, because it violated everything he held dear about physics. He believed in locality, the idea that what happens here shouldn't depend on what happens far away, at least not instantaneously. He believed in realism, the idea that particles have definite properties, whether or not anyone is measuring them. And he believed in completeness, the idea that a good theory should be able to describe reality fully, without gaps or ambiguity or irreducible randomness. Quantum entanglement, as understood through the Copenhagen interpretation, violates all 3 of these principles. And Einstein was simply not willing to give them up. For him, giving up realism and locality would be giving up on the very idea of physics as a description of objective reality. In a way, you can't blame him. These principles, locality, realism, completeness, aren't arbitrary preferences. They're the foundations on which Einstein built his greatest achievements: general relativity, special relativity, the photoelectric effect, the explanation of Brownian motion, his work on the statistical mechanics of radiation. All of these rely on the assumption that the universe is orderly, deterministic, and local. Quantum mechanics, with its superpositions and its entanglement and its intrinsic, irreducible randomness, seemed to Einstein like a step backward, a retreat from the goal of a complete, objective description of nature into a fog of probabilities and observer dependence. But nature, it turns out, doesn't care about what seems reasonable to us. The universe is under no obligation to make sense by our standards, and quantum entanglement, this strange, non-local correlation without communication, this connection that transcends space, is what nature actually does. We've tested it. We've confirmed it. We've built technology on it. and we're only beginning to understand what it implies about the deeper structure of reality. Here's what I find most remarkable about this whole story. Einstein was wrong about entanglement, but he was right to be bothered by it. The questions he asked, about the nature of reality, about what it means for particles to be correlated without communication, about whether quantum mechanics is the final word, are still the most important questions in the foundations of physics. Every interpretation of quantum mechanics is an attempt to answer questions Einstein raised. Every experiment testing Bell's inequality is a response to the challenge he laid down in 1935. In a very real sense, Einstein shaped the debate about entanglement, even though he ended up on the losing side. And there's something beautiful about that. Science doesn't progress only through right answers. It progresses through good questions. And Einstein asked the best questions anyone has ever asked about the quantum world. He didn't understand entanglement correctly, but he understood that it was important. He understood that it pointed to something deep and fundamental about the nature of reality. And he was right about that. The irony is that the depth and importance he sensed were even greater than he imagined. The story of quantum entanglement is, in a sense, a love story between physics and mystery. Every time we think we've pinned down what's happening, a new layer of strangeness reveals itself. We've gone from Einstein's spooky action at a distance, to Bell's theorem, to loophole-free experiments, to quantum teleportation, to the ER equals EPR conjecture. Each step taking us deeper into the mystery, each answer raising new questions. And the mystery isn't diminished by our understanding. If anything, it's deepened. The more we learn about entanglement, the stranger and more wonderful it becomes. And we're not done. Right now, in laboratories and on blackboards around the world, physicists are pushing further. They're entangling larger and larger systems, testing quantum mechanics at new scales, building the first quantum networks, and probing whether entanglement really does stitch space-time together. They're asking the next generation of questions, questions that Einstein and Bohr and Bell could never have imagined. What happens when you entangle a quantum computer with another quantum computer across the globe? Can entanglement survive near a black hole? Is the arrow of time itself connected to how entanglement spreads through a system? These are the questions that will define physics for the next century, and every one of them traces back, in some way, to that original argument between a stubborn man in Princeton and a pipe-smoking man in Copenhagen, each absolutely convinced that he understood what reality was, and each absolutely convinced that the other was wrong. And that's okay. That's how physics works at its best. The universe is not a puzzle with a neat solution printed on the back of the box. It's an endless unfolding, a perpetual revelation, a conversation between us and nature that never really ends. Every answer is the beginning of a new question. Every closed door opens onto a larger room. And entanglement, this strange, beautiful, impossible-seeming connection between distant particles, is one of the doors that, when we opened it, revealed a room far larger and more mysterious than anyone expected. So as you lie there tonight, in the quiet, with the world winding down around you, think about this. The particles in your body are part of a universe where distance might be an illusion, where connections transcend space, where the act of looking changes what you see. The atoms in your hand, the photons reaching your eyes from the lamp across the room, the electrons in your brain firing right now as you listen to these words. They all follow the rules of quantum mechanics. They can all, in principle, be entangled. They are part of this strange, interconnected quantum world that we've been exploring tonight. Einstein spent his last decades trying to make the universe make sense on his terms, and in a way, He succeeded, just not in the way he intended. By pushing against quantum mechanics, by insisting that it couldn't be the whole story, he forced physicists to think more deeply about what the theory actually meant. He forced them to clarify their ideas, to sharpen their arguments, to design experiments that could actually settle the question. And in doing so, he helped us understand the universe better, even when he was wrong, especially when he was wrong. Because sometimes the most important thing a scientist can do is refuse to accept an easy answer, to keep asking, "But why?" long after everyone else has moved on, to insist that there must be a deeper truth, even when the evidence points in a direction you don't like. Einstein did that his entire life, and the universe, as it always does, had the last word. The last word was, entanglement is real. The connections are real. The strangeness is real. And it's more beautiful than anything Einstein imagined. The moon is there when nobody looks at it, Albert. But the particles that make it up, the photons bouncing off its surface, the electrons in its atoms, the quarks inside its protons, those are playing by different rules than the ones you believed in. They're playing by quantum rules. And in the quantum world, reality is not what it seems. It's deeper. It's stranger. It's more connected than anything classical physics ever dreamed of. And that, I think, is a pretty wonderful thing to fall asleep thinking about. The light in your room, if there's any left, is made of photons. Each one is a quantum of the electromagnetic field, a tiny ripple in a field that pervades the entire universe. And right now, somewhere, two photons that were born from the same quantum event are still entangled, still connected, still correlated, still part of a single quantum state that spans whatever distance separates them. They might be in a lab in Vienna. They might be between a satellite and a ground station in China. They might be separated by inches or by light years. But in some deep quantum sense, they're not separate at all. They never were. That's entanglement. That's what Einstein couldn't accept. That's what the experiments confirmed. And that's what you're drifting off to sleep inside of. A universe where the connections between things are deeper and stranger and more real than they appear. A universe that Einstein helped us understand, even as he refused to believe in one of its most fundamental features. You know, there's a question that people sometimes ask when they hear about quantum entanglement for the first time. Does it mean everything is connected? It's a natural question, and it's one that physicists are a little uncomfortable with, because it sounds mystical, but in a very specific, very precise, very quantum mechanical sense. Yes, everything that has ever interacted is, in principle, entangled. Every photon that has bounced off your skin has become entangled with you. Every breath you've taken has involved quantum interactions between the molecules in the air and the molecules in your lungs. The entanglement is usually washed out almost instantly by decoherence. The information gets scrambled into the environment, diluted beyond any hope of recovery. But it's there, in principle, in the quantum record of the universe. Every interaction leaves a trace. Every particle that has touched another particle carries a faint, ghostly correlation with it. That's not mysticism. That's quantum mechanics. And the fact that it sounds mystical, the fact that the most rigorously tested theory in the history of science describes a universe where everything is subtly, inextricably interconnected, is one of the beautiful surprises of 20th century physics. Einstein would have resisted this picture with every fiber of his being. And yet, it's the picture that his own insights helped bring into focus. Sleep well, and if you dream of particles dancing in perfect correlation across the void, connected by nothing and everything at once, well, that's not a dream. That's just the universe being itself, quietly, beautifully, spookily. Good night.